welcome to another module in this massive open online course. Alright, so we are looking at quantization, alright, and we are looking at we have looked at several quantizers. We have looked at uniform quantizer, and we also looked at the Lloyd Max quantizer, which is the optimal quantizer. Alright, now let us look at a different quantization scheme, which is termed as companding. Alright, this is used for non-uniform quantization. Alright, so let us look at a different quantization scheme, which is termed as companding. Okay, this is termed as companding. This is termed as companding, which is used for non-uniform quantization. So, companding, and this is used for non-uniform quantization, correct. So, companding is used for non-uniform okay. So, this is used for non-uniform quantization. And what is the point of companding? The point of companding is that frequently we have signal which takes smaller amplitudes and larger amplitudes, alright, but it takes smaller amplitudes with a larger probability, alright, or we need a larger resolution, right, or we need greater accuracy at the smaller amplitudes, and the larger amplitudes which occur with less probability, we do not need a very high level of accuracy, alright. So, the point is that we have, let us say this is the dynamic range of the signal. Okay, let us look at this schematically. This is the dynamic range, this is the dynamic range of the signal, okay, and this is the increasing amplitude m, correct. And if you look at the smaller amplitudes, let us call this region as larger amplitude, these are larger amplitudes, and this is the region of smaller amplitudes. So, this is the region of smaller amplitudes, we have larger amplitudes. Okay. Now, in this region, the smaller amplitude region, we need higher accuracy. Okay. We need a higher accuracy. In this region, in the larger amplitude region, we can afford to be lax, all right, because these occur with low probability, or the reconstruction is not very sensitive to, basically because the amplitude is large, the reconstruction is not very sensitive to an error in the amplitude. So, one can be relatively more lax, or one can reconstruct it, or one can tolerate a higher level of error, which means the accuracy of quantization or the accuracy of reconstruction in this region of large amplitudes need not be very high. So, here one requires a lower accuracy of reconstruction. Remember, lower accuracy means you can tolerate. So, higher accuracy means quantization error has to be lower. So, lower quantization error. In this region, we can have a higher quantization error. In this region, we can have a higher quantization error. Okay. So, therefore, what we are so at the outset what we have to realize is that if you have a signal which is taking samples or values in a certain dynamic range, we do not need the same accuracy, the same level of accuracy in all the signal, in all the regions of the signal amplitude, all right. For the smaller amplitudes we need a higher level of accuracy, all right. For the larger amplitudes we need we can tolerate a higher quantization error, or basically we need a lower level of accuracy for reconstruction, which naturally means remember we said the quantization error is proportional to the size of the interval, that is the larger the interval, large number of samples are represented by the same threshold, so the quantization error increases. So larger the interval, which means the quantization error is higher. Therefore, the lower amplitude regions, since we need lower quantization error, we have lower quantization, which means we have to have quantization intervals which have very low quantization intervals of low size, that is the size of the quantization intervals, the length of the width of the quantization intervals has to be smaller at smaller amplitudes, all right, which means lower quantization error, and the width of these quantization error can be larger at larger amplitudes, which means a higher quantization error. That is the point, all right. So we have, again let us look at the dynamic range of the signal. If we place the quantization levels, this is the, all right, we can have quantization widths, that is quantization intervals smaller, and as progressively as the sample value increases, all right, the towards larger amplitudes these can be larger. For instance, if you can look at this, these are your larger, these are the larger quantization intervals, larger intervals, and these are smaller intervals. So this implies this region, this is a finer quantization, correct, this is quantized very finely. So this is a and if you can look at this, this is quantized very roughly or this is quantized very coarsely, okay. So this is coarser quantization interval. So this is a coarser quantization. So this is finer quantization, so the smaller intervals in the lower amplitude region which are quantized very finely, which means the width of the quantization intervals is small, alright, therefore quantization error is lower. If you look at the larger amplitude region, then the width of the quantization intervals is large, the quantization error is higher, therefore these are coarsely or these are roughly quantized, alright. So in summary, at lower amplitudes we need lower quantization error. This implies lower quantization errors implies smaller quantization, we need smaller quantization intervals. This implies higher accuracy. Higher accuracy of reconstruction, higher accuracy of reconstruction. When you say higher accuracy, automatically it means higher accuracy of reconstruction. On the other hand, at larger amplitudes, we can tolerate, right, quantization error, tolerate implies we need to have larger quantization. Implies we need to have larger quantization intervals. alright, which means lower accuracy of reconstruction. Which means we can have lower accuracy. Okay. Now, therefore, now if you can see, therefore, what we have, therefore, if you can look at this, the quantization, the width of the quantization in now if you look at this figure, you can see that the width of the quantization intervals is not uniform. You can see width of the quantization intervals is not uniform. Therefore, this is basically, this implies this is non-uniform quantization. This is a technique of non-uniform this is a technique of non-uniform quantization, because the width of the quantization intervals is different. Alright, different intervals have different widths. This is non-uniform quantization. Naturally, we said that because the quantization intervals in the lower amplitude region, they need to be finer, they need to have low widths, alright, and the quantization intervals in the larger amplitude region, in the large amplitude region need to have larger widths, alright, coarse quantization, alright. So, this we need non-uniform quantization, and companding is a way, right, companding is a way to achieve this non-uniform quantization. So, companding achieves so companding achieves so companding achieves non-uniform quantization. Okay. So, this is what companding achieves. So, companding achieves non-uniform quantization. Okay. So, for companding, right, companding which achieves non-uniform quantization, one can employ the mu law compressor. Alright, this is one of the techniques to compand. So, let us look at this, the mu law compressor. Okay, so let us look at the mu law compressor for companding. All right, and the mu law, that is an input output character. Remember, this companding is nothing but an input output mapping. It is a non-linear mapping from the input to the output, such that the smaller amplitude region is mapped to a larger width, all right, and the larger amplitude region corresponding to the larger amplitude is compressed, all right. That is the process of companding, all right. So, this is a transformation, and the transformation for the mu law compander or the mu law compressor, this is given as nu equals, well, log 1 plus mu times mod m divided by log 1 plus mu, and m lies in the range 0 less than or equal to, or 0 less than or equal to mod m less than or equal to 1. So, the dynamic range of the signal is normalized to 1, that is to lie between 0 and 1, alright. The basic meaning of that is whatever is the dynamic range of m, it is normalized, that is by dividing m by the maximum value of m, that is the maximum value of the amplitude, you can always normalize the samples to lie in the dynamic range 0 to 1, and then you can apply this transformation. Once you apply this transformation, quantize, and obviously while reconstruction you multiply back by the maximum value m, so that you reconstruct it to the original dynamic range, alright. So, this formula applies for a dynamic range of the signal level, that is the amplitude to 0 and 1, that is between magnitude of m lies between 0 and 1, m lies between minus 1 and 1. Okay. Now, this is basically your mu law compressor. Okay. So, and the mu law compressor, if you plot the mu law compressor, right, if we plot the mu law compressor, right. So, if we plot the mu law compressor. This is log 1 plus mu m. Now, of course, you can see at m equal to 0, it is not defined at as m tends to 0, right. So, now as m tends to 0, it tends to 0, at m equal to 0, this is 0, correct. Now, we are plotting this for m. So, this is m, or let us say magnitude of m equals 1. This is obviously at magnitude of m equal to 1, this is 1. So, the maximum value. So, it basically remaps magnitude of m lying in this interval 0 to 1, it remaps it to this interval 0 to 1, and the mapping is the log function. It is a concave mapping which is given as follows. It is a log function. Okay. So, this is the mu law quantizer, or the mu law compressor. This is the mu law compressor, and from this, so this is basically the log function, okay, which is a concave function. You can see that this is a just write this clearly, this is a concave function, and you can see from this, that is, if for instance, if you look at this region, correct, which corresponds to the smaller amplitudes. Now, this is mapped, you can see this region is mapped to this. So, this corresponding region, right, you can see this is expanded, right. You can see that this smaller amplitude, because of the concave nature of the log function, this is mapped, this is expanded at the output, all right, at the output of this compressor. It is spread, or basically it is expanded to a much larger region. Therefore, it will contain a when you quantize it, when you quantize the output of this mu law compressor, this region, right, contains a large number, will contain a large number or larger number of quantization intervals. Therefore, which implies that this amplitude region, this region corresponding to the smaller amplitudes will be quantized much more finely, all right. On the other hand, this entire region, if you look at this entire region corresponding to the larger amplitude. So, this is the region corresponding to the smaller amplitude which is expanded, and this is the region corresponding to the larger amplitude. If you look at this region corresponding to the larger amplitudes, this entire region is mapped to this small. So, this is compressed, correct. So, this is compressed. This is the large amplitude region. So, this large amplitude region, this is compressed. Smaller amplitude region, smaller amplitudes, this is expanded, all right. So, this expanded, which means it contains it will contain a larger number of quantization intervals, hence it is going to be finely quantized once you quantize the output of this compressor. Similarly, this larger amplitude region, which is compressed to a smaller region in the output, will contain much fewer number of quantization intervals, all right, and therefore, the resolution is going to be much smaller, all right, which means it is basically coarsely quantized. That is the whole point, all right. So, this implies this is expanded, this region is expanded, implies this is, well, this region is going to be finely quantized. This region is large amplitude region, this is compressed, this implies this is coarsely quantized. Okay. Now, right. So, this is coarsely quantized. Okay. And further, now if you look at this, interestingly, if you look at this characteristic for nu, that is, let us write this again, nu equals log 1 plus mu magnitude of m by log 1 plus nu. All right. Now, as mu tends to 0, of course, this becomes undefined because this is log 1 which is 0 divided by log 1. So, if you simply substitute mu equal to 0, then it becomes log 1 divided by log 1 which is 0 or 0, that is indeterminate. So, therefore, now we consider the limit nu tending to 0 or limit mu tending to 0 of this, that is for very small values of mu, this becomes log 1 plus mu magnitude m 1 plus mu. Well, we are going to use the approximation log 1 plus x limit x tending to 0 equals x, or log 1 plus x limit x tending to 0 log 1 plus x is approximately equal to x. So, this becomes limit mu tend to 0 log 1 plus mu mod m is approximately mu magnitude of m divided by log 1 plus mu is mu, which is basically, now you can see this limit is basically simply magnitude of m, which means that the characteristic is simply, that is your phi of magnitude of m, phi is the compressor, is simply magnitude of m, which means this characteristic is a linear characteristic, it is simply a straight line. Okay. Magnitude of m is simply mag to magnitude of m, right, which means that the or the samples are unaltered. All right. So, the samples are unaltered, okay, and therefore, this is simply a linear characteristic. Now, if you look at this, for mu equal to 0, this reduces to a linear characteristic. Okay. Therefore, if we plot this, correct, you again plot this thing in this box, remember, right, this is we are plotting log 1 plus mu magnitude m by log 1 plus mu. Now, if you plot this, what you will observe is that for mu equal to 0, it is a straight line. This is for mu equal to 0. As mu increases, it becomes more and more. So, this is basically the direction of increasing. This is basically the direction of increasing mu. As mu increases, it becomes more and more concave. All right. It becomes more and it becomes more, as mu increases, it becomes more concave. All right, which means basically this smaller amplitude region is mapped to an ever increasing, right, ever increasing portion of the output, and the larger amplitude region is progressively compressed even more and more, right. As the characteristic becomes more and more concave, the smaller amplitude region is expanded more and more, and the larger amplitude region is compressed more and more. All right. So, the resolution, that is the number of bits or the number of intervals, the smaller amplitude or the finer amplitudes improves progressively as mu increases, and the resolution or the accuracy of the larger amplitude region, that progressively shrinks as mu increase, all right. Okay. So, that is the mu law compressor, all right. For mu equal to 0, this is a linear. So, mu equal to 0, the characteristic is a linear characteristic, that is what we have already seen, okay. It is a linear. As mu increases, it becomes more which means as mu increases, which means more companding. As mu increases, there is more companding, that is more compression of the larger amplitudes. This implies more compression of larger amplitude region, and also more expansion of the smaller amplitude region. Okay. And also it is worth noting that this mu law compression, this compressor for quantization is used in the North American standards. Mu law compression is used in North American standards. This is used in North American standards. Okay. So, the mu law compression is used in North American standards. Okay. And in comparison, in contrast, there is also another compression standard, another compression or competing compression. This is known as the A law compressor. So, there is a mu law compressor, and we also have a A law. We also have an A law compressor, okay. And the A law compressor the expression is given as follows. The A law expression for the A law compressor, that is nu equals A magnitude m divided by 1 plus log A for 0 less than equal to m less than 1 by A, and it is 1 plus log A magnitude m magnitude m 1 plus log A 1 over A less than equal to magnitude m less than 1. Okay. Now, we can see in this A law quantizer that initially for some part in this region, basically 0 less than equal to magnitude m less than 1 over A, in this region it is linear, okay. And in after a certain threshold, that is 1 over A, in this portion it is logarithmic or it is concave. So, what we have is a linearly increasing characteristic or a linear increasing compander, so a certain portion, and then it starts becoming concave, that is where things start to be compressed, that is the larger amplitude region is progressively shrunk. So, if you plot this, this looks something like this. Again in our box corresponding to this 1 comma 1, magnitude of m is 1, magnitude of m is 1, correct. Now, until this point 1 over a, where a is suitably chosen, right, until this point it is linear. So, this will look something like this, and then it is logarithmic. And as a increases, this point progressively shifts, right, this 1 over a decreases, correct, 1 over a decreases and it progressively shifts. So, this is a times 1 or so, this becomes 1 over 1 plus log. So, this becomes, as this increases, this progressively shifts, correct. So, this becomes, so this progressively shifts, this point here, this is 1 over 1 plus log a, correct. When m, magnitude m equals 1 over a, this is 1 over 1 plus log a, therefore, this point comes down and it looks something like, it looks something like etc. and so on and so on, all right. So, as a increases, this point progressively shifts to the left, and this is basically your A law. This is basically your A law compressor. So, we have a mu law compressor, we have an A law compressor, and it is also again worth noting that this A law compressor is used in the European standards. So, the A law compressor is basically used in the European standards, all right. So, basically we have seen companding, right. Companding is nothing but we need different resolutions in different regions of the dynamic range, all right. For the smaller amplitude regions of the samples, we need finer quantization, and in the larger amplitudes we can tolerate coarse quantization, that is, we can tolerate a larger quantization error. Therefore, we choose, that is, rather than uniform quantization, we choose to quantize it non-uniformly, that is, having finer quantization in the smaller amplitude region and coarser in the larger amplitude region. For that purpose, we employ companding, all right, and we have seen two different kinds of compressors, all right, the mu law compressor and the A law compressor, all right, and the details have been described. Thank you very much.